All right. Hello, my name is Scott Hayter. Welcome to Business Calculus. I will be creating these videos to help you understand the material and hopefully prepare you for your homework. So, if you're nervous about taking a business calculus class, don't worry. I'm nervous as well. We're in this together. So, all right. Well, I guess let's get started. So, section 1.1, what is a function? So, you have a definition here. It's given in your textbook. I'm not super fond of it, but it says that a function is a rule that takes certain numbers as inputs and assigns each a definite output number. Okay, what does that actually mean? So, I think the best way to understand what a function is to start working with them and start seeing their different forms. So, usually we talk about a function in terms of a formula or a graph. So, for example, here's a formula. F of x equals minus x squared plus 7. And this gives us a way to get the y value if we have an x value. So, for example, if we want to know what the y value is when x is minus 2, then we'll just plug that in for x, and we'll plug that into the formula, and we'll just simplify it. We'll evaluate it. Make sure you remember that this minus sign on the outside, that gets applied last because of the order operation. So you square it, and then you multiply by minus 1. So we've got 4 times a minus 1, so this is actually negative 4. So be careful about that. All right, so we get f of minus 2 equals 3. Good. So this gives us a way to get the y value if we know the x value. But what if we want the x value when we know the y value? So this is the opposite. And this is the other thing that, kind of thing that you're asked a lot. So what if we know the y value is minus 9? By the way, I use, instead of saying f of x, I say y a lot because the function of x, that gives us the y value. That's like, this is what would go on the y-axis, right? The vertical axis. Okay, so let's say we know the y value is minus 9, and we want to know the x value. All right, so instead of plugging minus 9 in for the x, of course, we just plug it in for the y value, f of x, so the left-hand side of the formula. And then we just see if we can simplify everything out. We subtract 7 on both sides, so minus 9 minus 7 is minus 16. And then we multiply by minus 1. And we get to this step, 16 equals x squared, where we can take the square root of both sides. And when we take the square root, we need to remember to put a plus and a minus sign, because if it's a minus or a plus, when we square it, we still get the same number, right? So there are two solutions there. And the square root of 16 is 4. So there are two x values where the y value is minus 9 plus a minus 4. All right, so I hope that made sense. All right, so that's using a formula to describe a graph. The other very, very helpful way to talk about functions is in terms of their graph. So a lot of people feel comfortable when they see a formula for a function, but they never really felt comfortable describing a function by looking at its graph. So if you're in that position, don't worry, because that's kind of the whole point of this class. We will really practice and try to train ourselves to understand what exactly is a graph telling us. What is a graph telling us about the way a function is behaving, which is what calculus is really all about. Trying to understand the way a function is behaving. All right, so let's see. Let's first make sure that we can read values off a graph. This graph is given as kind of a grid, but imagine you have your x-axis here and your y-axis here. So what is f of 5 it says here f of 5 equals 3. Is that right? So let's see, f of 5, what is that? That's the y value when x is 5. So if I go when x is 5, so that's in between 4 and 6 here. And if I go up and find the graph, that's a y value of 3, right? So f of 5 equals 3. All right. Now, we have some layers of subtlety to show you in terms of how a function behaves. And this is the first kind of level. Okay, this is like the base level. All right. And it's about whether a function is positive or negative. All right, so we'll need to integrate these terms into our vocabulary when we talk about functions. So a function is positive, what does that mean? That means the y values are positive. A function is positive, a function is like the y values, right? Y equals f of x. That means, what does it mean for a y value to be positive on a graph? It means the y values are above the x-axis. The graph lies above the x-axis. So if here's the x-axis, okay, this down here would be like below the x-axis, and up here would be like above the x-axis, and we see that this graph is above the x-axis. For every x-coordinate, the y value is positive. So we would say that the function is positive for all the x values. A function is negative if it lies below the x-axis. Now, could a function be both positive and negative? Well, there might be places on the graph where it's positive, but then it might dip below the x-axis, and we would say for those x values, the function is negative. And where a function crosses through the x-axis, if a function crosses, let's say this graph just extended on down here through the x-axis, it would have to cross through y equals 0. The y value would have to be 0 at some point. And that's called, the x value where that y value is 0 is called a 0. So 0 is the x value where the y value is 0. So that's kind of the first level of subtlety. All right. So not too hard so far. I hope that made sense. Positive and negative. Now let's move on to the next level of subtlety, getting a little trickier here. Instead of positive or negative, this is the same. We just wanted to say that this function is positive. That was the point of the slide. Just the same slide, just saying this is a positive function. Okay, so that's level 1, like the base level. All right, so the next thing that we can say about a function is whether it's increasing or decreasing. And we say that a function is increasing, as you might expect. Remember, when we say function values, we're talking about y values. So if I say a function is increasing, that means the y values are increasing as we increase x. Now this is key. We're always looking at what happens to the y value as we go from left to right. Left to right. All right. As I go from left to right, I look at the y value and I see that it's going up. It's going up from left to right. That means that it's increasing on that interval for those x values. A function is decreasing if those y values go down from left to right. So during this bit here, the function is decreasing, right, as we go left to right. And then what happens over here, it starts increasing again, doesn't it? From left to right, it's going up. It's going up. Okay. So this doesn't have to do with the function being positive or negative, does it? Can a function be negative but increasing? Yeah, it can. So just imagine that this graph were just shifted down, so it were below this x-axis. But imagine the shape was still the same, so it would still be increasing for these x values here, and then it would be decreasing, and then it would be increasing again. All right. Uh, what would a constant function be like? That means the y values wouldn't change from left to right. What would that look like? Let's see, a constant function, would that just be a horizontal line? So what if this graph looked like a horizontal line? Would that be a constant function then? Yeah, that'd be a constant function. It's not increasing, it's not decreasing, it's just remaining constant. It's not changing. It's not changing. It's remaining the same. All right. And this function increases for, we kind of already talked about this, but increases for this bit, decreases for this bit, and then increases for this bit. So this is how we say it. We say it's increasing from these x values on this interval, and then it's and also it's increasing from on these x values, and then decreasing on these x values. All right, so that's the next level, and I believe we have one more. We have one more, but we're not going to talk about it just yet. Very soon we will. So the next thing that we're going to talk about is tables. So let's just make sure we can read off a table. I have a very high definition graphic for you here to look at. So let's just make sure that we can think about it in the same way that we think about formulas and graphs, and we can kind of do the same similar stuff that we can do for formulas and graphs, we can do for tables as well. So it says here that f of 6 is minus 1. So let's see, is that true? F of 6 is minus 1. So this gives x and f of x, so it's saying that when x is 6, y is minus 1. Is that true? So when x is 6, if I go over and I see that the y value is minus 1, yeah, that matches up. All right, so f of 6 is minus 1. Sometimes I'll say, or you might say, that f is minus 1 when x is 6. It's saying the same thing, but it's thinking about it differently is the key. So sometimes we're trying to emphasize something in particular, and we might say it a little bit differently. So you might say the same thing, but you just kind of change the way you say it to emphasize something. So, all right. So that's that. That's how to read off the notation from a table. It says here that the function is decreasing. We should say here probably that it appears to be decreasing. Now, we only have a few x values here and their corresponding y values. We don't have all their x values. I don't know what f of x is when x is minus 3 or minus 2.5 or maybe like square roots and stuff like that. That wasn't the case for like a formula. A formula, I can plug in any x value I want and get the y value, right? Or a graph, I can estimate any x value, I can estimate what the y value is. All right, but on this table, I'm only given 4 x values and their corresponding y values. So I had to go off that. What would it mean for the function to be decreasing? Remember, we always increase the x values. We always go from left to right. So as we increase the x values, what's happening to these y values? Going from 4 down to 0, down to -1, down to -3. These are decreasing. These are decreasing. So as we increase x, y is decreasing. So we'd see the function, the y values are decreasing. All right. And by the way, just in case you never thought about it before, there's 2 ways for a number to decrease. It can either become less positive, like it is here, or more negative. So the number 1 to 3, that's getting bigger, but they're negative, so it's like it's going down on that axis. Whenever you're going down on that y-axis, that's the y value decreasing. All right. So also there were 2 ways for a number to increase, right? It can become either more positive or less negative. Like, it's not on this graph here, but well, let's say if your value goes from -3 to -1, that's increasing. That's increasing because it's becoming less negative. So keep that in mind. All right, and to finish off 1.1, I have an example here for you. So let's see. The concentration of carbon dioxide, which we'll call C, and we'll write that as a function of T in the atmosphere. And we're going to assign units to the concentration, parts per million. And we'll define that as a function of the number of years since 2000. Now this is a very common way to define the time. Usually time is defined as either years since something, or hours since something, or months since something, or so forth. Usually you have a reference point when you define time, so you gotta look and find how it's defining time exactly. So, for example, time equals 0, what would that mean? That would be 0 years since 2000, so that would be in 2000. Time when t equals 5, that would be 5 years since 2000, so that would be 2005, and so forth. So usually we don't define t as being the actual year. It has a reference point. Okay, so let's interpret what it means to say that f of 15 equals 400. So let's see, f of 15 equals 400. So f of 15, what is 15? That's t, right? We've put in t, we put in 15 for t. So that means that 15 years since 2000, so that would be 2015. Okay, so in 2015, the function, which is the amount of carbon dioxide, is 400. All right. So could we say that in 2015 the concentration was 400 in parts per million of carbon dioxide? Yeah, we could say that. Notice here that this line is kind of to describe like how we got there, but this is what I'd like to see from you, something like this. So the concentration of carbon dioxide in 2015 was 400. So f of 15, that represents the concentration, that's the y value, at a particular x value. And notice here we have our units. I don't need units for 2015, that's just assumed to be the year 2015. But we don't just say 400 because it doesn't have any meaning when it's 400, the concentration being 400, what exactly? So we say parts per million. All right. How about B? It says, what is the meaning of f of 20? So f of 20. So f of 20, is that an x value or a y value? So f of 20. So it's the y value when the x value or t value is 20. All right, so this represents the concentration of carbon dioxide 20 years after 2000. So that would be in 2020, wouldn't it? So this is the amount of carbon dioxide in the air in 2020. Or maybe amount's not the best way to say it. Maybe concentration of carbon dioxide. Okay, just a little point here that we didn't actually find the number, right? What f of 20 is. And this is something that you'll need to get used to, is that we write expressions for things sometimes, like f of 20, without actually knowing what that number is, because we can still talk about what it means without actually knowing what the value is. Right, so f of 20, so it's the expression for the concentration. It's not the actual number. We don't have that, but we can still talk about that. Okay, so I believe that wraps it up for 1.1. We made it through it, first video. And yeah, so see if you can do your Wiley Plus homework for this section, and hopefully it goes smooth. Otherwise, you can let me know. All right. Have a good day.